Welcome to Hypothesis Testing Fundamentals, Validating ML Assumptions. In the world of machine learning, we often build models, compare their performance, and select features with certain expectations. But how do we know if these expectations are truly supported by data, or just random chance? This is where hypothesis testing comes in. It provides a robust statistical framework to make informed decisions and validate the assumptions underlying our ML projects, moving us beyond intuition to evidence-based conclusions. At its core, a hypothesis is simply a testable statement, or an educated guess about a phenomenon. In machine learning, a hypothesis could be something like, Model A performs better than Model B on this dataset, or this new feature significantly improves the prediction accuracy of our model. Every hypothesis test begins with what's called the null hypothesis, denoted as H. This is the default assumption, representing the status quo or no effect. Think of it as assuming innocence until proven guilty. In ML, H often states there is no difference, or no relationship. For instance, there is no significant difference in accuracy between Model A and Model B, or this feature has no impact on the target variable. Contrasting the null hypothesis is the alternative hypothesis, denoted as H. This is the statement you're trying to find evidence for, what you suspect might be true. If H suggests no difference, H proposes there a difference, or a significant effect. For example, Model A has significantly higher accuracy than Model B, or this feature have a significant impact on the target variable. The fundamental goal of hypothesis testing isn't to the alternative hypothesis directly. Instead, it's about evaluating the strength of the evidence, the null hypothesis. We assume the null is true, and then determine how likely our observed data would be under that assumption. If our data is highly unlikely given the null, we reject the null hypothesis. Key to this evaluation is the p-value. The p-value is the probability of observing data as extreme as, or more extreme than, what you actually observed. A small p-value indicates that your observed data would be very unlikely if the null hypothesis were true, thereby providing strong evidence against the null. To make a decision with the p-value, we need a significance level, often denoted by alpha. This is a predetermined threshold, typically 0.05 or 0.01, representing the maximum probability of rejecting a true null hypothesis that we are willing to accept. It's our acceptable risk of making a type 1 error. Our decision rule is straightforward. If the calculated p-value is less than or equal to our chosen significance level, we reject the null hypothesis. This suggests that the observed effect is statistically significant. If the p-value is greater than alpha, we fail to reject the null hypothesis, meaning we don't have enough evidence to claim a significant effect. Now, let's talk about errors. A type 1 error, also known as a false positive, occurs when you incorrectly reject a true null hypothesis. Imagine concluding that Model A is significantly better than Model B, when in reality, their performance is identical. The probability of making a type 1 error is equal to your significance level, alpha. Conversely, a type 2 error, or a false negative, happens when you fail to reject a false null hypothesis. This means you missed a real effect. For instance, concluding there's no significant difference between Model A and Model B, when Model A truly superior. The probability of a type 2 error is denoted by beta. The power of a test is directly related to type 2 errors. It's the probability of correctly rejecting a false null hypothesis, or in other words, the ability of your test to detect a real effect when one exists. Power is calculated as 1 minus beta. Increasing the power of a test typically involves increasing sample size or choosing a more sensitive test. Let's apply this to comparing model performance. Suppose we've trained two classification models, Model A and Model B, and we want to know if Model A is truly better. Our null hypothesis might be, there is no significant difference in accuracy between Model A and Model B. The alternative, Model A has significantly higher accuracy than Model B. We run a statistical test, like a paired t-test on cross-validation scores, get a p-value, and compare it to our alpha. If p-alpha, we can confidently say Model A is better. Hypothesis testing is also crucial for validating feature significance. For example, in a regression model, you might hypothesize that a particular feature, say customer age, has no linear relationship with the target variable sales. Your null hypothesis would state that the coefficient for customer age is 0. If the p-value associated with this coefficient is very low, you would reject the null, concluding that customer age is a statistically significant predictor. Understanding and applying hypothesis testing is fundamental for any serious machine learning practitioner. It enables us to move beyond mere observation to statistically sound conclusions, ensuring our model comparisons are robust, our feature selections are validated, and our machine learning assumptions are rigorously tested. This leads to more reliable models and more confident decision-making in real-world applications.